Hello.
Hi.
Доброе утро.
Доброе утро. А пока мы не начали, мы же группа 213, правда, да, в обратном порядке теперь?
Все верно.
Да. Спасибо.
15.
Ну, это не так важно, как я доску подпишу, но все-таки пусть порядок будет. Так, ну что ж. Very good. Вот. Okay. Well, so it's time to start, but there are 7 of us, which is not normal. So that's very bad. Still, let's start slowly, maybe. Well, I wanted to start. Okay, so maybe I will have to repeat it in the end, but let me first start with saying that I have not checked your tests yet, but I think I will be able to finish tomorrow. There is not much left. Generally, I want to say that most marks are positive, like almost every mark is positive, I mean higher than 4, and moreover many of marks are quite big, so overall I'm very satisfied. Well, and again, in details you will see when I finish checking them. So that being said, so last seminar we started talking about complex numbers, and we talked about algebraic form of complex numbers, their main form in some sense, and about operations one can do using it. This week, as far as I understand, lecture went through the notion of trigonometric form of a complex number and the properties of multiplication. Is that correct? I don't know. I see. Guys, anyone?
We just covered polynomials on the lecture.
Polynomials. Okay.
Yeah.
That's very bad. It means he kind of switched the order of lectures, maybe.
Mm-hmm. Unfortunately, I do not know whether we covered the geometric, form of
Trigonometric form.
trigonometric form.
Okay, let me quickly look into. It was on the previous lecture already. Wait.
Maybe.
Okay, it's interesting. So he went slightly quicker this year. Okay, I will have to adjust my plans for the next seminar then. But today still, I wish to talk about trigonometric form, the polar form, which was the previous time. So, okay, some of us are already here. Let's start. It goes as follows. If one has a number a plus bi, then it may be drawn on the plane using a point with coordinates a, b. Okay. Usually in algebra, we prefer thinking not about points, but about vectors to those points from 0. That's not important. Such a vector is the same as this point and vice versa. So if there is such a point, then one may consider this right triangle. And well, this side is A and this side is B by definition of coordinates. Then one may compute this side using Pythagoras theorem. I hope everyone still remembers it. So Pythagoras theorem claims this side is square root of a squared plus b squared. So this value is called the absolute value of a complex number. Absolute value. In Russian, that is модуль комплексного числа. Well, the same absolute value as we use with real numbers. So by definition, this is the square root of a squared plus b squared, where the square root means the normal square root with nothing interesting about it. The reason I say this explicitly is because we have something like, well, not really normal square roots. We will discuss them soon. But this one is a perfectly usual arithmetic square root. Okay, so there is, if we consider this number, there is well, the following thing can be done. I can extract this factor outside if I wish. I can write the same number like this. And this doesn't make much sense, but those are two numbers such that the following is automatically true. They are between -1 and +1 automatically. It is easy to see using some inequalities. I won't explain this. It's not important right now. We can believe in this. And the sum of their squares is automatically, if you open the brackets, it is automatically 1. Thus, those two numbers, this fraction and this fraction, can be considered a cosine and sine of some angle. I can consider the following system of equation of trigonometric equations, not linear equations, but trigonometric equations. And there is some angle phi that satisfies this system. When you solve such a system, you kind of solve one of them by knowing the cosine. You almost know the angle, for example. But there are some problems with, I'm sorry, knowing the cosine, you like get several possible values. And knowing the sign of the sine helps to distinguish which particular value is the one we need. So from such a pair of equations, you can get this phi you can find phi, it equals something, modulo 2 pi k, modulo 2 pi. I mean that you get some particular angle, but also if you add 2 pi, then the cosine and sine are still the same. And if you add 4 pi or 6 pi or minus 2 pi, the cosine and sine are still the same. So this angle is well defined up to addition of several copies of 2 pi. Okay. So the general solution is phi equals some constant plus 2 pi k, where k is any integer number. Okay. That was a quick recap on theory. Any questions here?
No.
So this set of all such numbers is denoted as argument of z with capital A. Capital A means we obtain not one number, but a set of many numbers. That is a traditional way of writing it. And while that's well good as a definition, it's not very nice in computations to talk about sets. So sometimes we have to use argument written with a small a. Argument of z is one of those numbers such that it belongs to some good interval. In different books, they pick different intervals. Sometimes it is from 0 to 2 pi, quite a logical one, and sometimes it is from minus pi to plus pi. And usually when you pick this one, you pick this border, and when you pick this, you kind of pick the positive one, but it doesn't really matter again. I don't remember which one the lecturer picked. I think this one, but I'm not sure.
First one, you.
Okay, so then I will try to follow this. However, whenever it is more convenient to use negative numbers, I will also use them. I will use the values of the angles that are the most appropriate for the particular problem. That is common sense. So, okay, so this formula we began with may be rewritten as follows: that if z equals a plus bi, it may be rewritten as absolute value of z times cosine of argument of z plus I times sine of argument of z. This cosine stands for this fraction a divided by square root, and this sine stands for this fraction b divided by square root. And for some reason here the tradition is that first you write the number and then you write I, and here again, well, historically there is a tradition that first you write I and then you write the sign. The reason is kind of that if you write I afterwards, it's not obvious what should be multiplied, the sign or the argument. So that's the reason why we write I before. Okay, again, it's not important, but that's a convention. Everyone does it like this. Sorry. Okay, so this form is called polar form, or more often trigonometric form of a complex number. So why is it interesting? Why would someone consider it? That's stupid. Well, before we go to this, let's first find the trigonometric form of several numbers, and then we will use it to see how it can be used in practice. So without further ado, let me copy a problem. So let us discuss the first question. So we have the number 5, the usual real number 5. Still, if it is real, it is also complex. It is a particular example of a complex number. How to find, well, its trigonometric form. Please provide ideas.
Just
Well,
first the argument.
So we need to find the absolute value and the argument. Okay, so what is the absolute value? How to find it?
well, because we have b equals 0, it is just square root of a square, which is just a. And
Okay, so it is square root of 5 squared plus 0 squared, which we can compute, and we can even not compute it as it is square root of a square. Okay.
yeah, so it is 5. Yeah.
Okay, so we see that for real numbers, this absolute value is the same as the usual absolute value. That's very nice. It's nice to extend the existing things, to not do something totally new, but just makes some additions to something that already existed. Okay, what about argument? We have properties for this argument that we know its cosine and sine. What is the cosine and what is the sine?
Well, sine will be 1. Oh, no.
Sine will be 0.
Okay, yes, so
Yeah,
cosine will be 1, that is 5 divided by 5. And sine is 0, so the trigonometric form starts to look like this. But I wish to know the angle, so we can solve this. I hope everyone knows what are the numbers whose cosine is 1. That is, phi equals 0 plus 2 pi k. Okay. Please note, all the angles I'm going to write in radians. Okay. Please forget degrees. That's like they remained in school. They will never return. Okay. So 0 plus 2 pi k. So I can write the trigonometric form, for example, as follows. I can pick any of those values, but typically we pick the most simple one and write the trigonometric form. Any questions? Okay, that's an easy example, I hope. Still, let me continue. I. What is the absolute value of I? Now this is something we don't know yet, something new.
Well, we know that a is 0 and b is 1.
Mm-hmm.
So it is, yeah, like this.
Mm-hmm. And this is, well,
1.
1. Okay. So I kinda has length of 1 in some sense, because the picture we can draw is as follows. It is the same as 1. So 1 goes here. Okay, this point is 1, 0. And I is 0, 1. It points in the different direction. It is like different than the real line. This line is called real line. In such pictures, this line is called imaginary line. So, but still, this thing has still length 1. Okay, very good. So this is 1 multiplied by 0 plus 1i. And we want to find the cosine and sine such that cosine is 0 and sine is 1. What is phi?
Pi divided by 2.
Pi over 2, you're right, thank you. So this is the series of solutions for this situation, which again, I hope you know well. And so I can finish here. So this is 1 multiplied by cosine of pi over 2 plus I sine of pi over 2. Any questions?
No.
Not yet.
Explain again about the imaginary, how to say it, line and the real one.
Well, if I draw complex numbers on a plane, then the complex numbers which are real, whose real part is something and imaginary part is 0, they all are on this horizontal line, horizontal axis. So it makes sense to call it the real line. Вещественная прямая.
Okay. And
well, the other one can be called imaginary line, imaginary axis.
okay,
Мнимая ось.
for example, 1 and 1 will be somewhere. No,
1 and 1?
да.
What do you mean?
No, точка 1 and 1.
Okay. The point with coordinates 1 and 1. Okay. It is, well, somewhere here. It's I don't want to draw it because there is something written here, but it will be here and it will be 1 plus I, the sum of those two vectors.
Okay.
So it is not real and not pure imaginary. It is in between. It is complex.
Yeah.
So let's try to do the next one then. -2. So let me be quick. -2. So the absolute value behaves the same way as with usual real numbers. So it is 2. Then this -1 has to go into cosine. And I hope everyone remembers their cosines. It works as follows. The corresponding angle is pi plus 2 pi k if we need it. Okay? Do I need to provide more details?
No, it's clear.
So those were like very basic examples. The next one is finally something, well, like not real or purely imaginary, but something in between. And so for this number, maybe it is obvious which factor we need here, but maybe it is not. Let me, one more time, do this explicitly. I have to raise -1 to the second power, and I have to raise square root of 3 to the second power. The result is 1 and 3, as far as I know. Okay. So that's square root of 4, that's 2. Thus, this is 2 multiplied by -1/2 plus square root of 3 over 2i. And you might see that, well, those numbers are, well, kind of well known to you. Those are cosines and sines of some angles. Only you need some precision to like not make mistakes which angle this is. The most easy way to do it is to use the trigonometric circle properly. So -1/2 looks like something like this, and square root of and this one is plus. So minus plus means we are in this area, and so it looks like something like this. Okay, this is the small leg of the right triangle, and this is the bigger one. So this angle is this angle.
So it is 2p divided by 3.
So it is 2 pi divided by 3. So this is cosine of 2 pi divided by 3 plus I sine of 2 pi divided by 3. So if you find that you don't remember all those cosines and sines, I heavily recommend you to go through the table of cosines and sines of like usual angles, the angles, well, the same angles you used in school, because we are going to need them quite a lot the next time, and maybe the time after the next one, and maybe in a short quiz soon, and maybe in a test in the end of the year, I mean semester. So please revise them. So still we are done with this exercise. Okay, very good. The final one is slightly more general. Oh, and it contains a misprint. It is not minus sine of alpha. It is minus I times sine of alpha, okay? Otherwise, that's simply stupid. I'm sorry, that's a misprint. Cosine of alpha minus I sine of alpha. Well, this looks like a trigonometric form of a number, and sometimes people make mistakes and think that it is, but it is not. The trigonometric form of a complex number contains a plus, and we have to somehow make it so that it has a plus. We need to somehow force it to have a plus here. So how to do this? I can rewrite this as like this, put this minus inside, but now again it is not a trigonometric form, because a trigonometric form is when you have a cosine and a sine of something, and here I have a cosine and minus sine. That's not proper. So how to find some other angle beta such that for beta this is the sine and this is the cosine?
Beta is equal minus a.
Indeed, it is easy to see that I make mistakes. It is easy to see that beta equals minus alpha works. And obviously I can change it again by copies of 2 pi. So I can continue that this is cosine of minus alpha plus I sine of minus alpha. This is the trigonometric form, the polar form of the number I began with. So its argument is minus alpha. This will be helpful soon in some problems. Questions?
And for example, if we just did calculated by definition, we would gain pretty much the same result. Like if we would think of a cosine like A and of sine like B.
Sorry?
Well, for example, if I wanted to calculate it by definition, like calculating first.
Yeah, I could compute the absolute value of this, right?
Yeah.
And that would be square root of cosine squared plus sine squared, which is lucky for us 1.
Oh, and then we have the same thing, yeah.
And then we have the same system of equations. I just skipped this because. Okay.
Yeah, okay, I see. Okay.
Thank you. Okay. Now we are ready to finally begin. We have done the how to say? Okay, I don't know the word. Still, we are now prepared to multiply something. So, let me consider the following example. Here is a product of 2 complex numbers, and we already know that we may open all the brackets and compute. However, I claim there is a more easy way to do this. In this particular example, maybe it is not much easier. It will be kind of comparable, but we have some more complicated examples later where it will be much easier to use trigonometric form. The idea is as follows. If there are two numbers, Z1 and Z2, in their trigonometric form like this, and someone multiplies them, then it is easy to see the result is obviously, well, you can change the order and put brackets, etc. So it is very easy to see that there is that we can put those absolute values together. And moreover, I don't know why I have written this. So you can multiply the absolute values separately. This is simply multiplying of some real numbers. We already know how to do this. And you can multiply the trigonometric parts separately. Moreover, someone has already done this for us, and it is in the lecture, for example. And you can see that the result is automatically the following. When you open those brackets, you will be able to use some trigonometric formulas to simplify the result, and it will become this. So the rule is that when you multiply complex numbers, their lengths, their absolute values multiply, and their arguments, their angles, add together. This is, well, like very nice rule. Adding angles is easy. For example, for this example, I can write the following. This is square root of 2 by this. This is, well, okay, it doesn't need to extract a factor. Okay. It is very easy when you remember the table of the cosines and sines that we usually use. It is very easy to not compute any absolute values, but simply like see the cosines and sines in those numbers. When I see -1 and +1, I immediately see that they need to be square roots of 2. So I extract this factor outside. Of course, I could compute that it is 1 squared plus 1 squared, that is 2. So the absolute value is square root of 2. So I can replace this by some cosines and sines. This part is
3 pi divided by 4.
Yeah, 3 pi divided by 4. Very good. And this part we had in the previous example, it was 2 pi over 3. And now the rule says that I have to add the angles. So the resulting angle is a 9 pi over 12 plus a 8 pi over 12. So the result is square root of cosine of 17 pi over 12 plus I sine of 17 pi over 12. So there are two things we can find from this example. Well, no, more than two. First of all, this was very easy. Again, I didn't do any hard work. I simply added two angles. Two, this was very long. It was easier to do all the operations, but there was lots of writing inside. Partially that's because I didn't skip any steps. For example, if I was not like trying to explain everything, I could write this step immediately after this step. Okay, and in fact, after this step, I would write this one. But the second reason is that, well, we kind of write it in a very long form. I will say a few words slightly later about that. That's the second thing. The third thing, we obtained an interesting answer. It is in some sense better than the usual one, in some sense worse. Indeed, if I still did open the brackets, I would obtain nothing like this. Let's do it. Let's waste a bit of time and open the brackets. I get 1/2, and from this I get I squared, so I get a minus, so minus square root of 3/2 plus minus 1/2 minus square root of 3/2i. So the theory claims that this number equals this number. So cosine. So on one hand, we can say that if this number kind of makes sense for us, we can do it this way. And if this number makes more sense for us, we can do it this way. Another thing we can see from this is that now we can find this cosine. It equals this divided by this. It wasn't obvious, I think, before we did this computation, was it? I think it was not. But now we know this cosine. Of course, I can find this cosine by cleverly using the formulas for the half of the angle. But still, I like the fact we were able to find it with a clever way. So in problems, when you obtain a cosine like this, which is not from the table of like good angles, you please know that you are allowed to leave them in the answer like this, unless it is explicitly said in the task that the result should be in algebraic form. Okay, that is kind of common sense, but every time there are some questions about it, so I want to say this explicitly. Okay, any questions?
No.
Not yet. Then, if there are none yet, let me do one more exercise and divide the same numbers. Now we remember that division was kind of nasty in algebraic form. We had to multiply by the conjugate, and the conjugate doesn't look really nice for this number, etc., etc. However, for this form, it is very easy. When I multiply, I add the number, add the angles together, so it automatically follows that when I divide, I subtract the angles. So the result is square root of 2 by cosine of 3 pi by 4 minus 2 pi over 3 plus I sine of 3 pi over 4 minus 2 pi over 3. The only thing that remains is to subtract numbers. That's the hardest part. That's 9/12 and that's 8/12, so 1/12 remains. Hooray! Okay. Now I need to think for a bit which way to move right now. So, well, okay, this makes sense. Now, I'm sorry, I just need to think for a moment. Okay. Now, please, now I want to make like a small part that is additional. It is not required to know, okay? It is not in the program, but it helps to write things down easier. So if you wish to write things down easier, I really recommend to learn this part, but you are allowed to skip it. The topic I want to talk about for 5 minutes is another form of complex numbers. It is almost the same as trigonometric form, but it is written in a different way. Let us look at the previous page, for example, at this computation. Please note that here I write this big bracket, but what is really important is 3 pi over 4. Everything else I already know. I know that it is going to be written cosine here. I know that it is going to be written plus I sine over here. And I know that, well, while I repeat the angle twice, it is going to be the same angle. This seems stupid to write everything down twice and write many letters around. Okay? Do I express my idea understandable enough?
Yeah.
Yeah.
Okay, so I wish to have some more compact way to write down this huge expression. Then here it will be more compact, here it will be more compact, here it will be more compact. A huge economy. And so there is such a notation. Well, there are 2 such notations, in fact. One of them was invented not long ago, as far as I understand, but still it exists. It is kind of an English notation. I don't, okay, so I don't meet it often. It is rarely used, but still it is still legal. So it uses a function with name cis, which means cosine I sine. Okay. Simply this is shorter than this, and that's it. If you use this notation, it already saves lots and lots of space and time spent writing. So again, I kinda slightly recommend it, but not really, because it is, again, it is some rare and obscure notation. No one uses it. Instead, there is another one, which is more weird, but it is widely used. It goes as follows. When you look at it, it is crazy. Because we don't know how to raise something in a complex power. What does it mean to take something I times, multiply something I times? That doesn't make sense. And it is quite hard to do so that it makes sense. And in your courses, there is no course devoted to complex analysis. So we're not going to learn at any moment how to properly do things like this. But if you think of this just as a notation, just that we write this to mean this, then it is extremely good and nice. Why do I say so? That's because, for example, the previous computation can be written as follows: e to the power of I 3 pi over 4 times e to the power of I 2 pi over 3 equals e to the power of I, and here is the sum. The rule that the angles add kind of follows from this notation. In reality, everything is backwards. We are allowed to use this notation only because this rule works. Otherwise, we wouldn't do it like this. But still, it is very nice that it kind of mnemonically helps you, that the rules are the same as the usual rules with powers. So this notation is called sometimes exponential notation. exponential form of a complex number. Okay, so for that number, for example, I would write square root of 2 times e to the power of I 17 pi over 12. And that's it. That's the answer for that problem. It is kind of, again, simply a short way to write down the same thing. Any question? But again, yeah, and in the following problems, while I like this notation, again, it is not part of the course, so I won't use it, okay? But for you, I recommend using it if it is not too hard. Okay, any questions for this part?
Can you repeat how exactly to pronounce the first one?
Pronounce this, I have no idea. I think it is cis, but maybe not.
Okay, and on Russian?
I've never heard it being used in Russian textbooks, so, and orally I haven't heard it. Again, I would pronounce cis, but it's up to you. I don't know. People rarely have to pronounce formulas. But we are online. Yeah. Okay. We often have. Okay. I don't know. Is this the only question? Fine. Okay. Then this was like a small, again, part, like step aside for those who wish to learn this. And now we return to the main course. And the next problem I want to solve is how to raise a number to a power. And my first favorite question is how to raise I to some power, for example, 77. Obviously, I can multiply I by itself and by itself and by itself until I am fed up with this exercise. That's not very hard, because if I do this, I will soon see that there is something interesting in the results. In fact, I to the fourth power, as we already, I think, discussed at some point, is +1. And you might remember from discrete mathematics that when some power is 1, then we know what to do next. What should we do next?
Like a cycle, maybe?
Yeah, so it is kind of a cycle here. So how to compute I to the 77th power?
We should look at the pattern. And
Okay, we
find
see the pattern, so what next?
We should divide 77 by 4.
Yeah, we divide 77 by 4. It is 4 times something plus 3. Right? If I subtract 3, I get no.
And it will be I in the power of 77 will be equal to the remainder.
Yeah.
No, not to the remainder, but I in the power of remainder.
Yeah, so I to the 76th power kind of cancels. And so the result is I to the first power in this particular example. And if it were like not the first power, but some other power still, it would be much easier to compute the 77th power. However, that is nice, but it works only for some simple numbers when this cycle exists and is short. I was able to find this cycle because I tried several times and I found it. But life is not so easy sometimes. Later we will see why this cycle exists, when it exists, etc. But right now, well, this seems like some luck was involved. So we want to have a method to find this power. So let's forget this happened and try once again. Using polar form. If I write I in its polar form, that is cosine of pi over 2 plus I sine of pi over 2, then when I multiply this 77 times, the absolute values multiply, they are 1, so nothing changes, and angles, arguments, get added together. So I get pi over 2 plus pi over 2 plus pi over 2 plus pi over 2, 77 times. Thus, the result is cosine of 77 pi over 2 plus I sine 77 pi over 2. What remains is computing the cosine and sine, and you will see that the result is I. So here, the cycle kind of appears in computing the cosine and sine themselves. And once again, I should note that in trigonometric in exponential notation, this looks even better. This is once again just a rule of working with powers. But once again, the next step requires simplifying this angle modulo 2 pi.
Sorry, can you explain one more time, please? How you powered cosine and sine into the power 77?
Yeah, I did not. Instead, I used the rule that when you multiply such brackets, their angles add. This rule, where is it? Here. This multiplied by this, this multiplied by this is automatically this cosine of the sum plus I sine of the sum. This rule means that when the angle is the same, when phi 1 and phi 2 are the same, then the angle gets like multiplied by 2, then by 3, by 4, etc.
Oh yeah, okay, thank you.
Mm-hmm. So this rule means that we have a very powerful way of raising to a power. I only need to multiply the angle by this number. That's easier. This powerful rule is called de Moivre's formula. Okay. My letters look not very good. Moivre. Okay. It's hard for me to write v and r so that they're separate, but okay, Moivre. Okay. His name is French, so they don't, so those E and S, they don't pronounce it, okay? And this O and I is pronounced UA. It's very easy to understand, right? Those are exactly the vowels that are not here, okay? So, and for some reason in Russian, we don't write de. I don't know why. Okay, so any questions about this power? Or I will go to another power, which is kind of more interesting and complicated.
Can you please show more interesting and complicated?
Yeah, you are bored. That's fine. It happens. Let's go to this power. Now, again, the number is not pure imaginary, but something more complex. Still, the process is kind of the same. I can write this as cosine of pi over 4 plus I sine of pi over 4. Because this is 1 over square root of 2, and this is 1 over square root of 2, and this square root of 2 helps to cancel everything, so we get 1 plus I. So now I can raise square root of 2 separately, and this expression with cosine separately. That's one of the rules of dealing with powers. And so this part can't be really simplified. This is, well, 2 to the power of n over 2 if you wish, but that's simply the same. And this part can be simplified. It is cosine of n pi over 4 plus I sine of n pi over 4. And that's it. Of course, one may next write cases depending on the remainder of n modulo 4 or 8. From this expression, it looks like 8, but it should be 4. No, maybe it should be 8. Okay, I'm slightly confused why this happened, but maybe I've made a mistake somewhere. No. Okay, I don't know what is happening, but okay, modulo 8 still. If you consider 8 cases, for each case you can compute the corresponding cosine and write down this answer as some particular value. This huge expression will be like 1 plus I for some values, or divided by square root of 2, or I, or simply 1, etc., etc., depending on different values of n. So,
And why do we have 8 variants?
well, because n, if n is 0, then this is 0. If it is 1, it is pi over 2. If it is 2, then it is pi over, pi over 4, then it is pi over 2, then 3 pi over 4, etc. So we have this, and then it returns back. When n equals 8, then this becomes 2 pi, which is the same as 0.
Okay.
So it kind of cycles. So the results will be, well,
Yeah. Okay.
1, this, etc. Okay. On the other hand, I can start with the same and use binomial formula that you should know from from calculus. Binomial formula.
1 power. Okay, you're right, Mark. Yes.
So we already know from the previous problem how to find powers of I. So I may rewrite this as following. This becomes multiplied by 1. Let me write several more steps. And so on. It is hard to write what happens at the end because I don't know about n, what is its remainder. So I will simply write plus, etc., meaning that it can be understood what happens later. So this expression can be split into real part, which is as follows. And imaginary part, which is as follows. So it looks like I have found, for example, as a particular corollary of my computations, that this equals 2 to the power n over 2, that is square root of 2 to the power of n, multiplied by cosine of n pi over 4. This left-hand side is something combinatorial, but somehow it equals an expression with cosine. Please note, there are no complex numbers here. This is it is an equality that is like about very much real mathematics. But we proved it using properties of complex numbers. And it looks like it would be hard to prove it somehow else, because it is strange and complicated. You might say that this can't happen because like this is an integer number and this thing can contain square roots of 2. But this part contains square roots of 2 if n is odd. And when n is odd, the cosine also contains square roots of 2. They cancel. So in fact, this number is integer. Okay, I hope you are like astonished by this formula. At least usually this happens. But even if not, well, okay, that's not a big deal. But I tried to surprise you as much as I could. This is one small example of the marvelous world complex numbers lead us to. But we will not discuss expressions like this any further. There are some interesting combinatorial type equations like this in textbooks, but they are not really relevant to our course, so I won't delve into this deeper. But if someone is interested, I recommend you to try to look into them. They are fun and interesting.
Sorry, can I have a question, please?
Very good.
Can you please show the second row of our Mauer's formula? As I got here, yes, example like I in power of n. We have 1 plus I in power of n, yes? The second example. The second
this
one,
and
yes.
this is the same. I did it with 2 different ways. Okay, so
I want about the second example. I know that they are same, but in the во второй строчке там в конце I в степени n. Нет, не здесь. Второй, да, здесь I в степени n. Здесь.
Okay. Yes.
But why we write here I in power of n if we like making у нас I в степени возрастает, а 1 уменьшается. Все. Thank you.
Very good. Ну, может, было в обратном порядке, это не важно. Whatever. Okay. Yeah, that is the use of binomial formula, not the Mauer's formula, but binomial formula. Okay. Okay, very well. Then let me maybe continue with other stuff, but give me a second to find out the proper way. Well, let me maybe then continue like this. You might remember that we discussed this problem last time, and we solved it by applying brute force, which is our favorite method, but still it has some disadvantages. So let us be clever today and solve this problem again using trigonometric form of complex numbers. Suppose z is r times cosine of phi plus I sine of phi for some values of r and phi. In other words, let's represent z in its trigonometric form. Then we have r cubed times cosine of 3 phi plus I sine of 3 phi equals 1. This number is z cubed. Okay. I raised r to the 3rd power, and here I multiply the angle by 3. means, once again, de Moivre's formula. But then this number also has trigonometric form. This form is as follows.
Sorry, how you obtained 1?
Again, that's what I'm solving. Z cubed equals 1.
Ah, okay.
Don't worry. I'm trying to find such Z, solving an equation. So now I'm trying to find for which r and phi this equals this. Well, I think
R is 1 and phi is 0.
no.
No?
No. R cubed is 1. Cosine of 3 phi is cosine of 0. And sine of 3 phi is sine of 0. Let's solve this, but with precision. So R is a real positive number. Absolute value is length of something. It is real and positive. So it means that if we know its cube, we know R itself. This part is okay. But if cosine of something equals another cosine, this doesn't mean that the angle are the same. The angles are the same, right? It requires thinking. So what can we say about angles if their cosines are equal and their sines are equal? Angles have the same cosine and the same sine.
We are just in one, how to say it, четверть. Нет?
Not,
Если мы на круг посмотрим.
no.
45,
There are
for-
different
there are 45
angles.
degrees. 45 degrees or just opposite one plus
No,
B.
45. I don't. Okay. I don't understand what you are trying to say, but 45 degrees, that is pi over 4, that is one particular direction, but what does it have to do with our problem? I don't understand.
They have similar arguments.
That's better, but arguments are, well, those angles.
So it has to be plus minus pi over 4 plus p.
Plus minus what plus what?
Plus or minus p over 4 plus p.
Y pi over 4 and y pi.
Maybe pi over 2?
Okay, but, lots of guesses.
Pi over 4 because cosine and sine can be in the same coordinate only if it is pi over 4.
But cosine and sine are not the same. One of them is 1 and another is 0. What do you mean the same? They're not the same. So again, this, so 3 phi, let's forget about 3. 3 phi is something like which we analyze together. 3 phi is some angle and its cosine is the same as cosine of 0. And its sine is again the same as sine of 0. What does it tell us about 3 phi? Well, we've already done this.
It
Just
equals
0
0.
plus pi k.
0
plus
plus
2k.
2 pi k.
Pi k, yeah.
Okay. There are many solutions, but all of them differ by 2 pi. But obviously, one of the solutions is 0. If you put 0 here, then those are equal. That's obvious. I just wanted to emphasize that that's not the only solution. We may change it. And in the previous problems, this plus 2 pi k never mattered. We wrote it, but immediately forgot it, because after that, in many problems, we took the cosine of this value and immediately this part disappeared. But in this problem, this part will be important, because now I divide by 3. And now I claim that for different values of k, I get different numbers from this answer. If k equals 0, then r equals 1, phi equals 0. So z equals 1 times 1 plus 0 I. That's 1. That is one of the cubic roots. Indeed, this number cubed equals 1. But if k equals 1, then phi equals 2 pi over 3, which leads me to the number minus 1/2 plus square root of 3 over 2i. And you might remember that last time we obtained that this number cubed is 1. Today I obtained it using a different method. And this method is more useful generally. Last time we were lucky that something worked and we were able to find everything. But this method works more often. It is more general. If k equals 2, phi is 4 pi over 3, and z is, well, it requires some thinking, but let me just say that the result is this. You can think about cosines and sines and verify this. And what happens if k equals 3? Then phi is 6 pi over 3, which is 2 pi. So its cosine is the same as for 0, and its sine is the same as for 0. So we obtain a cycle. We obtained infinitely many solutions for the angle, but the numbers that those solutions give us repeat. Different k give us the same numbers again and again and again. So in the result, there are 3 possible values for z. This, this, and this. Questions? Okay, so in this particular example, I kind of obtained myself a general way of finding roots of complex numbers. I have kind of obtained a cubic root from the number 1. And in fact, now that I understand how it works, I'm able to write a general formula for finding a root of nth power from the number 1. Indeed, by following the same logic, I can easily write that r in some power, well, that this equals this. Then I will be able to write that r equals 1 and n phi equals 0 plus 2 pi k. Then I will be able to write that phi equals 2 pi k over n. And finally, I can say that I can use k not from z, but it is enough to use k from 0 to k to n minus 1, because when k equals n, this becomes 2 pi, n over n cancels. And that's the same as 0. And when k is n plus 1, then this is 2 pi plus 2 pi over n. So it is the same as 1, etc. They cycle. Okay? So nth root of 1 is gives us many answers. It is cosine, well, it is 1 cosine of pi over n plus I sine, sorry, 2 pi over n, 2 pi over n, cosine of 4 pi over n plus I sine of 4 pi over n, etc. N different numbers. And so in study of complex numbers, there is a tradition that when we write a root of a number, it is not one number, but a set of numbers. Taking a root is unfortunately not a function, but like a multifunction. It provides many outputs. For example, square root of 1 in this notation, when we think of 1 as a complex number, then it is not 1, but it is plus minus 1. This is slightly unusual, unfortunately, but that's life. The reason why, so with real numbers, we were able to pick one of two answers and say it is better. We will denote this number as square root. Unfortunately, with complex numbers, there is no good way to do this. It is kind of hard for me to prove that there is no good way to do something. How would I prove this? I can't explain that something is impossible. But practice shows that no one is able to invent such a good way. Again, there are some reasons for that, but they're kind of hard to explain. So I will skip this part. Okay, I think the main part is finished here. So any more questions here?
How we get that the absolute value was 1 in that
Well,
one?
So for the absolute value, its nth power is 1 and r is a real positive number. So, so it means that it is nth root of 1, where this nth root means a different thing than this nth root. Again, it is kind of inconvenient that by the same sign, we denote two different ways, two different things, but this is a complex root, and this is an arithmetic root, the usual one. Okay. And,
yeah, okay, but like if that in power n just was equal to 2, like what is the absolute value? Will be?
That's a good question. We don't have much time, but and so we're going to continue the topic of roots next time. But right now, for example, if z, say, cubed equals, say, -2, then I can write that z equals cubic root of 2, whereby cubic root of 2, again, I mean the arithmetic cubic root, the usual one that we already understand, multiplied by cosine of something plus I sine of something, where this something is, I think, going to be discussed maybe next time. Well, if I put +2, then it is 2 pi k over n, where k is 0, 1, 2. Okay, let me use +2. And next time we're going to discuss -2 and many more problems of this sort.
Like we take just module and then put it onto the square root of just.
Well, not
root.
necessarily square root, but any root.
Yeah,
that we
in root
require.
just in power n. Yeah. Okay.
Yeah, so again, it is kind of strange situation where we explain how to take roots using roots themselves. I could write a stupid formula. Cubic root of 2 equals cubic root of 2 multiplied by the way, n is 3. By this. This formula is stupid because those two signs, again, mean different things. This is complex root. And this is arithmetic root, okay? So I will try to avoid such formulas where the same thing appears twice, but sometimes they are unavoidable. You just have to use common sense to understand what we mean in this context by a root. Life would be easier if people invented two different signs for this, but for some reason, historically, it is the same sign. That's life. Any questions?
Okay, can you show just one more time the first page of our seminar?
The very first page?
Yeah. Just.
Okay. It was long ago.
Yeah, I know. Yeah, thank you very much.
But you know, if you are trying to photo it or something, you can use the link. I have sent it.
Can get.
I have sent it in the beginning, and maybe someone can repeat it if you need.
Yeah, okay. Thank you.
Can you please resend this link?
Okay, I'm trying to, but
okay.
It doesn't work for me. It is easier. I clicked it. Okay, I can resend it this way, but unfortunately, using chat in Zoom is very not nice when you are making a presentation. So I try to not use chat as much as possible. If at some point you find that some of the old, I advise you to have those links somewhere in your group chat. But if at some point you see that you have lost some of them, write me and I will find them and maybe post them on Wiki.
It will be very nice.
If I post them on Wiki?
Yes.
Okay, I will try to not forget this. It's not very hard. It's just hard to not forget doing this because there is lots of things not to forget to do, and that's one more of them. Okay, so yeah, another question?
May I guess about the -2? Is it somehow connected with complex conjugate or no?
No.
No. Okay.
Not yet. No. Okay, so next time we are going to continue talking about roots and then about solving equations and stuff like that. And one final thing I want to say before everyone leaves. In the beginning, I said that I hope to check your tests tomorrow, but maybe it will happen like the day after tomorrow. But I hope to be done tomorrow. I've done like most part already. Okay.
Okay, thank you.
Good luck.
Thank you very much. Have a
If
nice
there
day.
are any questions, don't hesitate to write me.
Thank you. Goodbye.
Thank you. Goodbye.